The standard deviation is the positive square root of the variance and is symbolized as an S. Sometimes it is written as SD. Here you see the formula with the blue rectangle around it, showing that S sub x equals the square root of sigma, or the total of all x minus x bars squared, divided by n minus 1. When you look at the formula, you'll see that the standard deviation is basically a measure of the average of the deviations of all the scores away from the mean. Now, they have been squared, added, and so on, but at the heart, they are still deviations. As we'll see in Chapter 6, we can understand the standard deviation in terms of how many scores fall no more than one standard deviation above or below the mean. For most normal distributions, we can say that about 2/3 or 67% of the observations lie within one standard deviation of the mean. As we see in the graphic on the right, a small or low standard deviation value indicates that the data points tend to be very close, whereas a high or larger standard deviation value indicates the data points are spread out over a large range of values. Here we see examples of standard deviations from the mean, and you can start to understand how standard deviations are useful in telling us the percentage of values that fall in a certain range. Take a look at the small standard deviation and consider how many more values are likely to fall very close to the mean, since the standard deviation is smaller and thus closer to the mean. A large standard deviation allows for values to remain within one standard deviation, but be further away from the mean. The percentages you see are standard for any normal distribution. With regard to formulae, we see that there is an alternative way to find the sample variance, thus giving us an alternative way to find the sample standard deviation. The answer we obtained by using either formula should be exactly the same. When we talk about degrees of freedom, we're really talking about n minus 1 as the divisor. That's an example, at least. To obtain an unbiased estimate of the population deviation, we use n minus 1 as the divisor instead of n. Here we see a clip from the book. Earlier, I used the divisor of n minus 1 instead of n for the calculation of the variance in the standard deviation. The quantity n minus 1 is referred to as the degrees of freedom and represents an adjustment to the sample size to account for the fact that we are working with sample values. That's pretty much the essence of degrees of freedom. To be a bit more specific in this situation, in estimating the sample standard deviation, we first had to calculate and use x bar, or the mean, to estimate the population mean, which is symbolized by mu. Because we did that, we need to adjust the sample size accordingly. A box plot is also called a box-and-whisker plot. Constructing a box plot begins with defining the median location of a set of scores. The number of scores is represented such a way that n plus 1 divided by 2 equals the median location. The median location as a whole number is a whole number if it is odd, but it is a decimal number when when n is even. Let me repeat that. The median location is a whole number if n is odd, but it is a decimal number when n is even. A horizontal line is drawn at the median. Since that is the 50th percentile, hinges are drawn at the 25th and 75th percentiles. Lines called whiskers are drawn from the top and bottom of the box to the farthest point or value that is no more than 1.5 times the interquartile range. An asterisk is drawn for every value that lies beyond the whiskers. If the median falls halfway between the lower quartile and upper quartile points, we can guess that the data are somewhat normally distributed. If not, there may be some skew. When a whisker is no longer on top or to the right, it is positively skewed. When a whisker is longer on top or to the right, it is positively skewed, and the median will show up closer to the left or bottom, or 25th percentile. This section is about a normal distribution, which I've already mentioned. I want to try to explain why we are so interested in distributions in general. The critical thing that you need to know is that there's a link between distributions and probabilities. If we know something about the distribution of events, we know something about the probability that one of those events is likely to occur. Look at the pie chart. If we know that 18.3% of users are likely to use Internet Explorer, can we not make a prediction that almost 1 in 5 users in the future will use Internet Explorer? Of course, things could change, but this is based on what we know so far. We'll give the distribution regarding being late for class. These are the most common reasons given. If a student approaches me at the end of class and wants to tell me why they were late, I have some pretty good guesses based on the data as to why they were late, but I'm not exactly sure I trust this particular data. Here we see on the next slide a distribution from which is drawn a normal bell curve. How well do you think it fits the bell curve? In other words, is it normally distributed? Would you say that it's unimodal or bimodal? If it is a normal distribution, is it skewed or is it kurtotic? And what is kurtotic? We've learned about skew, but not kurtosis. To be kurtotic, we would see that the data are spiking here, such that we're going out of the normal bell curve shape in a different way. We could have platykurtic, which is spiking above the normal bell height or pitch, or mesokurtic, which is when that peak is much lower. What can we use about what we know so far of the standard deviation and the mean to determine if this is normally distributed? Refer back to slide 39, and you'll see that 68% of any normal distribution falls within one standard deviation of the mean. What would be the upper and lower limits for this 68%? With normal distributions, we can speak a common language. They're standardized to some degree. As the example says, a 90% 100 question exam is the same as getting 45 items right on a 50 item exam, or 9 items right on a 10 question exam. They also all compute to being A's. The common language that we are referring to is in terms of standardization. It involves transforming all values to a z-score based on their standard deviation. We'll talk more about z-scores in just a minute.